making tea in the background. It's okay. She'll be dead in a second. So I'm going to talk to you about graphs. And graphs are a collection of two sets, a set of vertices and a set of edges, all connecting to each other. Well, the vertices are all connected to each other by the edges. So I have about 10 things to know. And one of the things is a bonus, just a little side note. But so the first thing is the definition of a vertice, which is the separate points given in a set. So examples are A, B, C, and D. Those are all the vertices of a set in a graph. And then number 2 are the edges, which is also in the definition of a graph, which is one of the basic components. And it's the lines connecting the vertices in a graph, such as right here, connecting A and B, B and C, C to D, and D and A. And then we have when two edges are incident to each other, it's when two edges are sharing the same vertice. So like right here, will you come over here and like zoom in on this, please? Can you see it okay? Yeah?
Yes.
Okay, so right here, these two edges are incident to each other because they share the same vertice of A. And then, number 4, are when two vertices are adjacent to each other, it's when they share a edge. So A and B are sharing this edge right here, so those two would be adjacent to each other. 4, okay, now, number 5, if I can find it, here it is. It's a cycle. Why are you laughing? It's a cycle, which is when like a loop is created. Loop, because there's another definition that is a loop, but this is just for general terms. It's when a loop around the graph starting and ending at the same vertex. So right here, we start at point B, and we go from B to C, C to D, D to E, E to A, and then A to B. So we started and ended all at the same point. Okay, so number 5 is done. Number 6 is the degree of a vertex, which is the number of edges incident to that vertex. So right here, we have vertex A, and it has 3 edges, all corresponding to this one vertex. So it has a degree of 3. And there's a special case where if you have a loop, which we'll get to the definition in a moment, it contributes to 2 degrees within the loop. So the vertex, if it has one loop and then two edges that correspond to it, it'd have a degree of 4. So basically you can think of it as like the number of intersections. That's how I think about it, not generally the number of edges. Because as another bonus, a loop is just one edge. Number 7 is a loop, which is where a point starts and ends at the same, an edge starts and ends at the same point. So right here we have a loop to vertex A. Just goes woo, and that would make A have a degree of 2. Good job.
How does it go?
This is a loop.
And it goes what?
It goes loop.
No.
Woo!
Yeah, there you go.
So A would have a degree of 2. Number 8 is a walk, and it's a way to go from one vertice to another along edges, and it can overlap. So you can go over the same number of edges multiple times to go throughout the graph. So here's an example. Okay, so we start here. We go down, up, around, all the way down, up and around, and back up. So we started and ended at the same point, but we also overlapped on our edges. That's allowed. But when it's not allowed is when it is a path. And a path is the same as a walk, but you can't go along edges more than once. Once you've used it, you can't go back. Can't backtrack. So we start here, we just go around the square and end at the same point. You can't go from A to B to A to D to A. You can't do that. That's wrong. Number 10 is the length of a cycle, which is the number of edges used to get from one point to another within the cycle. So let's say we go from A, B, C, D, and E. Say we go from A to B, B to C, C to D, D to E, and E to A. Be a length of 6. Because you go around 6 edges. Number 10, and then another bonus, is an Euler trail, which is a walk. So our walk was a way to go from one vertex to another, and it can overlap. So an Euler trail can overlap, but it has to go along every edge in the cycle. Wait. walk containing every edge. Yeah, okay, it's a walk. Yeah, see? A walk containing every edge only one time. Stop. Okay, now we have some example problems. Let's put those off to the side. Come over here. Come over here. Come over here. You're ridiculous. Okay, problem number 1. I have drawn this graph out for you. And we have edge. We have to find an edge, 2 adjacent vertices, a vertex of a degree 4, and a cycle of a length 5. So, here, not me, here. So, one edge would be, say, A to B, because that right there would be the edge. And then 2 adjacent vertices would be E to D, because remember, adjacent vertices are 2 vertices connected by the same edge, so that would be right here. They share one edge, E and D. And then a vertex of a 4th degree would be A, because A has 4 intersections, 4 intersection points. See that? 1, 2, 3, 4. And then a cycle of length 5 would be just going around this little pentagram here. So B to C, C to D, D to E, and E to A.
A pentagram.
And A to B. And it had 1, 2,
That's
3,
the devil.
4, 5. Stop. And that would complete your cycle. So, now we have problem 2, which is a little bit simpler, but also one of the basic concepts that you should probably remember, is finding 2 paths. So right here you can find 2 pathways. Right here just by going from A to B, B to C, and C to A. So that's one path, and that length would be 3, because that's 3 edges used up.